Hello everyone, this is Monica Lupion, and today we will go through an example about one-dimension steady-state conduction. Just a reminder about the methodology on problem solving. Please read the problem carefully and spend a few minutes, if needed, paying attention to the information provided and making sure that you understand everything that is mentioned in the statement. Then it's very useful if you can draw a diagram with the main elements of the problem, like a snapshot. Write down the equations, very important, especially for exams and quizzes. So then you can show, even if you make a mistake during the calculation, you can show the structure that you know the equations that you need to apply and you know how to apply the equations. Then go through the calculations with a special consideration about the units. And finally, please box a solution. So today's example, it's about a fin, an extended surface. So please stop your video now and spend a few minutes reading the problem through. Water and air flows are separated by a square steel plane, a wall with a length of 1 meter and a thickness of 3 millimeters. To increase the heat transfer rate between these fluids, Mr. John Cole decided to add straight rectangular fins of 1.25 millimeters thickness and 2.5 centimeters length, spaced 2 centimeters apart. The steel has a thermoconductivity of 45.1 watts per meter per Kelvin. The air side and water side heat transfer coefficients might be assumed constant with values of 15 and 250 watts square meter per Kelvin respectively. Please calculate the percentage change in total heat transfer when fins are added on air side. So in order to solve this problem, first of all, I will draw a very simple diagram. We have the plane wall, which is 1 meter, 1 meter. This is the water side and this is the air side. And now the information provided by the problem. We have a convective heat transfer coefficient in the water side is equal to 250 watts per square meter per Kelvin. The coefficient in the air side is 15 watt square meter Kelvin. Thermoconductivity K is equal to 45.1 watt meter Kelvin. And the plane wall has a thickness of 3 millimeters. So we need to determine the change in the heat rate transfer when we add fins. Okay, so first of all, we're gonna calculate the heat rate when there is no fin. We know the general formula is the heat rate is equal to delta T over the sum of the resistances. In the case of this plain wall without any fins, we have to consider the convective resistance in the water side, the conduction through the wall, and the convection in the air side. In total, there are 3 different resistances: air 1 in the water side, air 2 corresponding to conduction, and 3 corresponding to the convection in the air side. We know that the thermal resistance for convection is equal to the inverse of the convective heat transfer coefficient in the water side times the total area of the plane wall. This is equal to 1 over 250 watt square meter per Kelvin times the total area, which is 1 square meter. This is equal to 0.004 Kelvin watt. What about the thermal resistance related to the conduction? R2, this is equal to the thickness, delta X, over the thermal conductivity K times the total area. This is equal to the thickness, which is 3 millimeters, times 10 minus 3 meter per millimeter, so we converted the units, over the thermal conductivity, which is 45.1 watt meter Kelvin, times the total area, which is 1 square meter, and this is equal to 0.1234065 Kelvin watt. And finally, resistance number 3, which is related to conduction in the air side. This is equal to the inverse of the heat transfer coefficient times the total area. This is equal to 1 over, the coefficient is 15 watt square meter Kelvin, and the total area is 1 square meter, and this is equal to 0.0601 Kelvin watt. So the heat transfer, using this formula here, heat rate is equal to delta T times the sum of the different resistances 1, 2, and 3. So the heat rate is equal to delta T over 0.004 plus 0.1234065 plus 0.0601. You do the calculations, and this is 1413 delta T watts. Okay, so this is the, we can call it heat rate 1. And this is when we don't have any fins added.